All right, so you just finished watching a video over potential energy diagrams, and by now you should understand this. All reactions are either endothermic or exothermic reactions. Either they are absorbing energy or releasing energy as the reactions occur. Another piece to this is understanding that different materials, based on how they're designed or based on their molecular composition, can absorb different amounts of energy before it starts to degrade, right? If I took a lighter and I put a piece of metal under a flame, it's not going to just disintegrate and fall apart like maybe a piece of paper would, because the specific heat of those particular materials are different from each other. And so this is taking thermo to the next level and looking at calculating how different types of materials absorb energies. Specific heat, as the video that I sent you on Friday said, is the amount of energy. Specific heat. Sorry, my spelling's incorrect. Is the amount of energy required to raise the temperature or needed to raise the temperature of a material by 1 degree Celsius. The amount of energy needed to increase the temp of that material by 1 degree Celsius. Here's an example, and a very common example, is looking at the specific heat of water, H2O. Water has a specific heat of 4.18 joules per gram Celsius. What does that mean? That if I had 1 gram of water, I would need 4.18 joules of energy. Let's say, okay, let me backtrack. Let's say I had 1 gram of water at 70 degrees Celsius. I would need 4.18 joules of energy to increase the temperature to 71 degrees Celsius. That's what we're looking at. This specific heat is unique for every substance. In fact, we can use specific heat to identify the composition of unknown materials. If we discovered a new material and we wanted to know what its composition was, then we could use thermochemistry to determine the elements of those based on how much energy it's able to absorb. Water is a unique one because we learned in our solutions unit that water has hydrogen bonds and it's polar, and those hydrogen bonds require some energy to begin to break up and can absorb quite a bit of energy. That's why our oceans are so important to keep us from, on land, from the vegetation and us from just frying up and deteriorating. It's the ocean water is able to absorb quite a bit of energy from the sun to help protect our environment and help us. So I'm using water as the example because we're going to be using this 4.18 in these problems. And, it's good just to familiarize yourself with some common information that you're going to need probably later on if you continue to study science or chemistry. This is a constant specific for water. I'm sorry, I left off one little part of this unit. It's joules per gram Celsius. My apologies. All right, if we were to look at the specific heat of aluminum, aluminum specific heat is 0.902 joules per gram Celsius. So it requires way more energy to heat up water than it would aluminum, and we can attest to that from our own personal experiences, right? Especially if you cook or you love to barbecue and you use aluminum, on a grill or something. Aluminum heats up really quickly, so compared to waters, especially. So we can identify different elements or substances based on their specific heat. The specific heat formula is Q equals MC delta T. All right, so let's break down these variables a little bit more. Q is heat energy. That's different from temperature. Heat energy is going to be the total, if we're using specific heat and we're looking at a particular substance, we can look at and calculate the total amount of heat energy that was utilized by that substance or taken in by that substance. And it depends on the temperature. All right, M is equal to the mass. How much of that mass of that substance, how much of that substance do we have? For example, if I had water, and let's say I had, I don't know, a little beaker with 10 milliliters. And then I had, let's say, another container with 500 milliliters of water. It's still going to essentially require the same amount of energy to get these to increase. But this one is going to take, it's not going to take as long to heat up because it's a lot less. So the masses will affect the energy absorption as well. That's one way to look at it. Okay, C is the specific heat constant. And for different materials, it's a different number. You can find charts and lists of this. Here is a chart I found with different substances, and we can see various specific heat. So if I pull it up a little bit closer, we can see that the specific heat for vegetable oil is 2 joules per gram Celsius, whereas nickel is 0.44 joules per gram Celsius. So if I had 1 gram of nickel, I would need 0.44 joules of energy to increase the temperature to 26 degrees Celsius. Okay, so specific heat constants are specific for different materials, different substances, and they're a given. We can classify substances based on their specific heat. I'm going to keep repeating that over and over because that's the key takeaway here. All right, and then the last variable that we have is delta T. Delta is, in science, means a change in. It means change. So when we're looking at a delta of something, usually we're taking the final of that, whatever it is, and subtracting it from whatever the initial was. So in this case, in order to calculate our delta T, we would take the final temperature, and I'm just write a little F for final, minus where we started. We're not worried where it ended. We want to know the total change. We just need to know the change in the temperature, because that change in temperature is what's going to give us our value for our total heat energy change, our Q. So our initial temperature. So recap in this formula real quick. We have Q equals MC delta T. That Q is the total heat energy. The M, the mass. C is the specific heat constant. It's specific for every different substance that exists. And delta T is the overall temperature change, the final temperature minus the initial temperature. Let's take a look at a couple of problems. All right, I'm going to bring our formula over. We're not going to work all these problems. We're just going to work the first two. Q equals MC delta T. Number one, how much heat must be absorbed by 375 grams of water? That's important, right? Knowing that it's water, because why? Because we need to know what our C is going to be. To raise its temperature by 25 degrees Celsius. All right. So let's start breaking down our variables. We're going to be using Q equals MC delta T. Let's see what we have. It's saying that how much heat. So we want to know how much heat altogether is going to be absorbed if I have 375 grams of water. How much heat altogether? So that should tell us right away that our Q is our X. That's what we need to solve for. M, we boxed our M. It says we have 375 grams of water. 375 grams. The fact that it says water, like I said, lets us know what our C is, because water has a specific heat capacity, and that is 4.18 joules per gram Celsius. And then our delta T. Now, in some problems, it's going to say if your initial temperature is this, or if your final temperature is this, and so on. And then you have to calculate, okay, my final temperature minus my initial temperature. But in this problem, it tells us the total change in temperature is 25. So we don't need to do any extra calculation here. The total change, if I had taken the final temperature and minus the initial temperature, then my answer for delta T would be 25. So we're looking at the overall change, so 25 degrees Celsius. We don't need to do any extra calculation. And now I'm just plugging in. Now, real quick, before we start plugging in, I like to just plug them in and solve for X. Some of you might do better if you rearrange your equation first. Now, it works out well because we're solving for Q. So we don't need to rearrange our equation. But if you were solving for, let's say, mass, and then you might want to rearrange your problem for M and then plug in. But it's working out well for us already, so we just need to plug in to our formula. We have X is equal to our mass, which is 375 G's, times our specific heat for water, which is 4.18. And I'm kind of cheating here because I'm not including my units, which you should. And then our delta T was 25. So all we're going to do is just multiply all of those numbers together. If I did 375 times 4.18 times 25, I would end up with 39,187.5 joules of energy. That's a really big number. That's a lot of energy. And a lot of times we won't use joules, we'll actually use kilojoules. And so if I was going to convert 39,187.5 joules to kilojoules, then I just move this over 3 where my decimal is, 1, 2, 3. And so it would be 39.1875 kilojoules. Or we could just say 39.1 kilojoules. Remember, these are the same numbers. They're equal to each other. The reason why scientists like to use something more like this is because most of their calculations are dealing with all kinds of numbers. Dealing with really large numbers like this makes calculating more tedious and just more room for error when you're having to account for every single little digit. And so typically scientists will try to simplify their numbers as small as possible by converting their units. So we went from joules to kilojoules. We just moved the decimal over 3. It doesn't matter. I'm just, again, introducing you to material that will most likely come up later on as you continue taking science courses and things like that. Let's take a look at number 2. Number 2 says, what mass of water can be heated from 25 degrees Celsius to 50 degrees Celsius by the addition of 2,825 joules? Okay. So clearly from the very beginning of the problem, we know that we are solving for M. So let's extract all the other variables first. Q. It says by the addition of 2,825 joules. That's going to be the total amount of energy needed to raise that temperature, that change in temperature of a particular mass of water. And so this 2,825 J is our Q. That's the total change. So 2,825 joules of energy. All right. M is what we're solving for. M is our X. What is the mass? What mass of water? So that's what we're solving for. We have C. It tells us of water, so we're still dealing with water. We're going to use 4.18 joules per gram Celsius. And then our delta T. Now, in this problem, it doesn't tell us what our overall change is. Instead, we see our initial temperature and our final temperature. So we need to do a little bit extra work here. Our final temperature is 50 minus our initial temperature, which was 25. So our total delta T is 25 degrees Celsius. All right, let's rearrange our problem so that we're solving for M. If I have Q equals MC delta T, and this is what I'm solving for, how do we get rid of this so that we're solving we get M by itself? Well, if I'm multiplying M times C times delta T, I need to do opposite of that. So I need to divide both sides by C delta T. C delta T. These cancel each other out. So for our equation, we're going to use M equals Q divided by C delta T. You don't have to do that. I'm just showing you, sometimes it just makes it easier. You definitely need to be able to manipulate to manipulate your variables so that you can easily calculate what you're trying to calculate for, whatever your x is. All right, so we already know, we already have our formula we're going to use. We just need to plug in. So our Q was 2,825 joules divided by C, which is 4.18. Oh, that looks sloppy. Let me go back. Okay. So 4.18 times our total, our delta T, which we already calculated to be 25. Our total change in temperature was 25 degrees Celsius. All right, plug that into our calculator. Remember, order of operations will sometimes play a factor. So I'm going to do 2,825 divided by, all right. Okay, so if I did 2,825 divided by 4.18 times 25, my answer, or our answer, is going to be 27.03. 27.03 what? You need to go back and you need to remember, you cannot just give me a number. That number means nothing. What is that number representing? Well, in our problem, it was asking for the mass. So our mass unit is going to be grams. All right, recap again. What happened in our problem? We were looking at a problem that said, how much mass would I have needed, or how much mass of water can be heated to raise the temperature a total of 25 degrees, and when that happened, the total energy exchange was 2,825 joules. So what we were calculating was for the mass. If I had 27.03 grams of water and I changed the temperature 25 degrees Celsius, the total amount of energy that would be absorbed would be 2,825 joules of energy. All right, so that is calculating specific heat. Specific heat, remember, is looking at how different materials require a different amount of energy to raise the temperature by 1 degree Celsius. We can use Q equals MC delta T to calculate or determine total amount of energy that would be absorbed based on how much of that substance I have and based on how much of that how much we're changing the temperature. All right, bears, make sure you took notes. You will be seeing a quiz over this and potential energy diagrams tomorrow. We have one more week of school left, not a whole lot of time. Please make sure that you are taking care of your work, taking your notes. Use your notes for your quizzes. You're going to be having a quiz here soon, like I said, and you're almost there at the end. You're doing a great job. We'll talk to you soon.